Hello everyone, today we are going to explain the basics of IP routing. Previously, we have actually talked about many things related to IP, such as our IP addresses. In a typical data communication network, we might have many IP subnets. Our Layer 3 network devices need to exchange some routes and data between these IP subnets. These devices have routing capabilities and can forward our data across subnets. Routing, as we say, is actually a fundamental element in data communication. It is the process of selecting paths within our network, and through these paths, data can be sent to our destination. In this lesson, we will introduce the basic concept of routing. So, what do we need to understand today? Here, we need to learn about the basic principles of a router, how a router selects the optimal route, and the best path. In addition to this, we will also cover some aspects of the routing table and the functions of advanced routing, which we will explore in detail. First, let's discuss the basic concept of routing. Within the entire IP network. Although we have previously learned about IP addresses, we need to understand what the fundamental concept of routing looks like. Now, in this diagram, we have many devices, and these devices are all Layer 3 devices. The IP address is a unique identifier for nodes on our network, essentially serving as a locator. We say that each IP address belongs to a unique subnet, and each subnet belongs to different areas within the network. To enable communication between different subnet areas of our IP addresses, we need routing to tell us how to reach the destination. This route is the shortest, because, as we can see here, we can choose to go this way, or we can choose to go that way. Both are possible. Each route can actually reach our destination, but here, we need to choose the best route. This is essentially what routing is about. Routing involves many routes, and it determines how I should proceed now. In this context, routing is actually used to guide the path information for forwarding our data packets. Routing devices, such as our routers, are network devices that send our data packets to the destination address based on the routing. Common routing devices include our routers. These routing devices maintain and store routing information in a table called a routing table. We often say that if we want to go somewhere, we need a map in our mind. How do we look at this map? How do we think about it? Certainly, we construct this map using various methods, for example, from small to large. Your mom or dad tells you how to get to school, and in your mind, there will be a map, showing how to get to any place you know. So if someone on the street asks you, for example, how to get to a certain building, you would tell them that to reach this building, we can go through the road on the left or the road on the right. Now, in this process, we can use these roads to reach our destination. Now, in this context, our devices work the same way. In the future, if a device needs to forward these data packets, then how do our devices handle these data packets now? Forward them according to the routing table. If I have the route in my table, I will help you forward it. If I don't have it, then I'm sorry, I can't do it. So what do they mainly look at? Is it the source IP address or the destination IP address? Here, it is definitely the destination IP address. Because, for example, I have a package now and the delivery person needs to help me deliver this package to the recipient I want it sent to. In this case, he definitely won't pay much attention to who sent the package. Instead, he focuses more on who the item is ultimately going to be sent to. So, it's the same here. All devices actually forward based on our destination. The gateway and the routers in between, after receiving the IP data packet, will choose an appropriate path based on these destination addresses, and then forward our data packet. Then send it to the next device. Each device forwards one by one, meaning it sends from one to another. As for the last router on the path, we will address it based on our Layer 2, which means finding the MAC address. Finding means within this, on my link, where exactly is my destination. Finally, the data packet is forwarded to our target host, and this process of transmission is what we call routing. That is to say, forwarding is based on our destination, and these intermediate devices select the optimal forwarding path from their own routing tables. The routing entries include our outgoing interface and the next hop. These are used to forward our IP value to the corresponding next device. Now, let's take a look at the routing information here, which includes our destination. Here, it is used to identify a subnet and mask for the destination, and together with our destination, it identifies the subnet. It also includes our outgoing interface, meaning if I want to go to 10.1.1.0, which of my own interfaces should I use to exit? For example, the 000 interface, HCIE, and our next hop, meaning if I want to reach this destination now, what is my next step? This is often the IP address of the interface directly connected to you, for example, 1.1.1.2. I need to use this next hop to find 10.1.1.0. Here, the outgoing interface is which of my own router's interfaces I use to send out, and the next hop indicates which next device my router uses to forward the data packet to the destination network segment. In this context, the next set of devices is used for forwarding IP addresses, and forwarding our IP data packets cannot be determined solely by our outgoing interface. Therefore, we must specify the next device. Here, if, during this process, I am connected through a switch in this network, everything goes out from my interface. So, after it goes out from my interface, what happens next? To which device should it be sent? So here I need to specify the next hop. In this context, this information identifies the destination subnet and specifies a forwarding path for our data packets. If during this process we now see this routing information, in the future, they will all form an IP address table. Within this IP address table, routes can be discovered in many ways. The router will select the best route to place in our routing table. Of course, when I say the best route, I mean that its subnet and mask are the same for the same one. If I learn through different methods, for example, here your mom tells you the route to school, and your dad also tells you the route to school. Here, you will choose one person to listen to and put it in your table. We say that through different methods, when we hear this information, we can choose one to place in our routing table, selecting the best one. Now, in this context, the router will forward IP packets based on the routes in the routing table. The router manages these path information by managing their IP routing table, and the router is in. A routing table may contain many routing entries, but the routing table only includes the optimal routes, not all routes. For example, if I'm going to school, there are many routes, or if I'm going to the office, there are many routes. But I only choose one. I think it's the shortest, and I think this route is the best, so I put it in my mental map and follow this route in the future. Routers manage routing information by managing the routing entries in these routing tables. This is the basic concept of routing. So, how are these routing entries generated? Here, we can see that the conditions for their generation are divided into three types. They are direct, static, and dynamic. Here, we mentioned that the router needs to forward packets based on its routing table. And to achieve routing table forwarding according to these routes, it needs to obtain the routes. Through these three methods, they can learn routing entries. First, let's talk about direct routes. A direct route is a route generated by the device itself and points to a local network. In this context, for example, if I want to assign an address to my interface, let's say my interface IP address is 20.1.1.024. This is my 001 subnet, and my 000 subnet is the 10.1.1.024 subnet. Now, as long as during this process, this is the route on my own device, it will be generated in my table. Its protocol is direct, which means I learned it through a direct connection, representing a route on my own device. Besides this, we also have static routes, which need to be manually configured by our administrator. For example, the direct route here is like no one needs to tell you how to get to your own home. You were born there, so you naturally know the route to your house. On the other hand, static routes are like someone telling you how to get to school, or how to get to work. In this case, someone tells you which interface you should use to go to 31.1.024. I will manually point it out to you. And this is often configured manually by the network administrator. And what about our dynamic routing? In this process, it's like having a navigation system. It calculates the optimal route for you. For example, in this context, our OSPF, ISIS, BGP. When learned in the future, the protocol will tell you it was learned through OSPF. We often say that the routing table is formed in these three ways: direct, static, and dynamic. First, in this process, let's talk about direct connections. Although it needs to be generated, the conditions for its generation are not that simple. It's not just created casually. In this context, direct routing. If we want to form one, it is first automatically generated by the device and points to the local network we are directly connected to. Here, when our router is the last router to forward data, it directly matches this direct route, and the router will forward the IP address to our destination host. When our data packet uses these direct routes, the purpose of forwarding the data packet is that the IP and the router's outgoing interface are within the same subnet. For example, in this scenario, if I want to transmit data in the future, let's say there is a computer at 20.11 and it wants to find someone at 10.0.1. Now, during this process, after the computer sends out this data, I hit. After receiving the RTB, now that I'm here, I will check the table. I see that this is a direct route on me, so which interface should I send it out from? I will send it out from my 000 interface, and here I can help others reach their destination. Helping others to forward. So how is a direct route generated? Not all interfaces with configured IP addresses can generate direct routes. First of all, you need to pay attention that the IP address of your interface must be fully configured. And during this process, my own interface must be in an up state, meaning it is in a normal operational state. And we cannot manually shut it down, nor can it be malfunctioning. Besides this, the interface on the other end that I am directly connected to must also be in an up state. It cannot be down, because during this process, if the other end is down and I am directly connected to it, I can sense it. So what will I do with my own state at this time? It will also become down. So during this process, it will not appear in my routing table. In other words, either of our interfaces, my own interface and the interface I am connected to, both need to be in an up state, and my interface must be configured with an IP address. Only then will a directly connected route be generated in my routing table. If my JSON00 interface encounters a problem, it will not appear in my routing table, and this direct route will fail to be generated. Now, during this process, if we have multiple routes, how do we select the most optimal path? Let's first take a look at what the routing table looks like. Inside, there are several very important parameters. In the future, if you want to check the routing table on the device, we need to use a command, display IP routing table. It will then tell us that currently I have 6 entries. There are 6 routes to the destination network. Here, it will indicate the destination you want to route to, its subnet, and how it synthesizes the destination network. Besides this, there is also our protocol, which means the method through which I learned it, and pre here refers to the priority of our route, as well as our cost value. Flex flag, as well as the next hop and our outgoing interface. Now, let's go through them one by one. First, in this context, if our destination and subnet mask represent specifying a particular destination and mask, it means it exists in my routing table. For example, in this process, I have now obtained the destination network, which could be a computer, a router, or any device, and its host subnet. For example, if the destination is 1.1.1.1 with a subnet mask of 255.2255.255.0, then the network segment where this computer or device is located is 1.1.1.0. In the future, I will look in my routing table to see if this network segment exists and forward it according to the interface of this network segment. Besides this, there's also our protocol. This refers to the type of protocol used in our routing, meaning how our router learns the routes. Besides this, there is also our priority, which represents the priority of our routing protocol. If we learn the same route through static or direct connection, we will choose one based on priority and not include both in our routing table. Because in our network, there may be multiple paths to the same destination. The routes have different next hops and outgoing interfaces. These routes may be discovered by different routing protocols or manually configured by us. The router will choose the route with the lowest priority as the optimal route. If in the future we cannot determine the optimal route through priority comparison, we will then choose the one with the lowest cost value as our optimal route. In addition to this, we also have what we call the next hop. The next hop refers to the route to the destination network on my device, specifically the next hop address. This means I need to forward this to the next device. And what is the IP address of that device? Apart from this, we also have our interface, which means from which local interface on my device I will forward this packet. Now, let's first talk about my priority. Here, when our router learns the same subnet through different routing protocols, if these routes have the same destination network segment and our wildcards, then our router will first compare the priority of these protocols and routes and select the path with the lowest routing priority. In this process, whichever has the lowest priority will be selected first, meaning the smaller the better. Ultimately, the best one is placed in our routing table. For example, if there is a route here, I will check whether its destination and wildcard are the same. If they are different, even if it's our network segment or if either the network or the mask is different, I will still place it in my routing table. Suppose there is a 192.168.1.024 and another one is 25. Both of these will be placed in our routing table. If both are 192.168.1.024, then at this point, it means they are the same. In the case where both are the same, I will compare their priority. The smaller the priority, the better. Whichever is smaller, I will place it in my routing table. Here, let's talk about its comparison process. For example, right now we have an RTA here, and it finds that there are two routes to 10.0.0LL30. One is static and the other is OSPF. In this context, we consider the prefix. Our network address and our wildcard mask are the same, so we look at their priority. In this context, each router has its own priority. For example, static routes have a priority of 60, while OSPF has a priority of 10 here. We are 10 while static is 60. I will compare which one is smaller, and certainly our 10 is smaller. OSPF will be placed in our routing table, while our static route will not be included. If all our routes are learned through OSPF, then our priorities are the same, both being 10 and cannot be distinguished. At this point, our RTA here needs to consider another parameter. At this point, RTA has learned two addresses with the same destination through OSPF, both being 10.0.0.030. In this case, the priority result cannot be determined because both are learned through OSPF. At this time, I will compare the cost values, meaning I will compare their costs. The criteria for measuring these two routes are different. If one is 11 and the other is 20, the smaller one is preferred. We will place the one with the smaller cost into the routing table, while the one with a cost of 20 will be discarded and not placed in the routing table if it is directly connected. Or rather, they are static, and they do not have the option of a cost value. This parameter is only available in our dynamic routing protocols such as OSPF, ISIS, or BGP, whereas directly connected and static routes do not have it. What is the priority? Here we can see that the priority for directly connected routes is 0. The priority for static routes is 60. And for our dynamic routing protocols such as OSPF, there is a distinction between internal and external routes. For internal routes, the priority is 10, and for external routes, it is 150. This table lists the priorities of some common routing protocols. However, in reality, there are more routing protocols, which we will gradually learn about in subsequent lessons. For now, just get familiar with this information. Now, in this context, if our routes are discovered through the same routing protocol, and there are multiple routes to the same destination, and if these routes have the same priority, then we will select the optimal route based on their cost values. In this context, the metric cost value of a route represents the cost of reaching the destination network segment. Common metrics include hop count, bandwidth, delay, cost, load, and reliability as measurement standards. For example, if we want to go to the United States, there are various ways to get there. For instance, we can take a ship or a plane, and here we need to consider what points everyone cares about. If, in this case, everyone wants to enjoy more scenery along the way, then we can take a cruise ship to visit various countries. However, if everyone is more concerned about time and is in a hurry, then we would choose to fly. So, in this context, the criteria for evaluation are different, and each protocol has its own evaluation standard. In this case, if I learn different routes through the same protocol, I will compare their cost values. If the cost value of one is lower, it will be placed in my routing table. This cost value is also referred to as the metric. Now, in this context, suppose there is a route. As before, we will first check whether the destination and the wildcard are the same. If they are different, then both will be placed in my routing table. If they are the same, I will first compare our priorities. If I can determine that one is smaller and one is larger, the smaller one will be placed in our routing table. If the priorities cannot be distinguished, then at this point we compare the cost value or metric and choose the lower one to place in our routing table. To select the optimal route, here it will also perform routing forwarding based on the path. For instance, in this process we can see that if a router receives an IP packet, it will determine the destination network of the packet and compare it with all the routes in our local routing table until the longest match principle is found. Here it follows the longest match principle, meaning my table is already set up, calculated through various routing protocols. In the future, I will forward based on this table. For example, in this process now, I have an IP address, and in the future, I want to reach the destination IP 172.16.2.1. So this. Sometimes I will choose the longest mask in my routing entries. That best matches mine. For example, here, we say my IP address is 172.16.2.1. First of all, it does not belong to our 172.16.1.0 network segment. So this is passed. Besides this, we see that it belongs to the 2.0 network segment. And here we say it also belongs to the 172.16.0.16 network segment. Both of these are valid, But during this process, you need to take a look. If both are valid, what will I choose? I will choose the one with the longest subnet mask. When we convert this subnet mask to decimal, its length is 24. The subnet mask below, when converted, is 16. So, since 16 is smaller than 24, we choose 24. This means that, in the end, we will go through 172.16.2. The subnet mask is 255.255.255.0. For this route, I will perform a forwarding. If you still don't understand, let's look at a few examples. For instance, right now, the destination we want to reach is 192.168.2.2. During this process, in the routing table of our RTA router, there are two routes to 192.168. 2.2, one has a subnet mask of 16, and the other has a subnet mask of 24. According to the longest prefix match principle, ITcertification, we should choose the one with the subnet mask of 24 for forwarding. In this context, it helps us reach the destination, because a longer prefix often means fewer host bits, which implies greater precision. Therefore, it will choose the one with the longer subnet mask for forwarding. As for 3.0, it's simply because 2.2 does not belong to the 3.0 network segment. So when we conduct an election between these two, if one is 16 and the other is 24, we choose the one with the longer subnet mask. Now, if in this context, my address needs to go to 192.168.3.2. How many routes to 3.2 are there in our RTA's routing table? First of all, it is not going to. The 2.0 network segment. So here we need to choose between the two routes, 192.168.1.0.16 and 192.168.3.0.24. Now one has a 16 mask and the other has a 24 mask. According to the longest prefix match principle, which one will be chosen? The 24 will be chosen because it has a larger mask. Therefore, we will forward to the next hop, which is the device at 30.1.1.2 to help us forward the traffic. Now, in this process of routing and forwarding, each device actually needs to check its own table. For example, in this scenario, I have a host with a computer here, and it wants to reach the destination 40.1.1.2. It will send the request to its gateway. Once the gateway receives it, it will check its own table to see if it has the route. If it does, it will forward it for you. If not, then sorry, I can't help you forward it. Then it will check its routing table to see if there is a route to 40.0.1, 1.024 in this subnet. And my surprise, I want to send it to 20.1.1.2 from my own 000 interface now. After sending it out here, when it reaches R also needs to check its own routing table. Every device needs to check its own routing table. Every device needs to see if I recognize this destination address. Then when checking its own routing table, it will find out. Now in this process, my routing table has this 40.1.024, and I need to send it to our 30.12. The next hop is this 0.1. So from my 0.1 interface, I send it out. After sending it out, when it reaches R3 also needs to check its own table. So in this case, we need to check if the routing table has an entry for the next hop. I send it to 40.1.1 from my 0.1 interface. Based on these routing table entries, we can correctly send these routes to our destination. When the data returns, it also needs to have a return path. The device will send it back to its gateway, HCIA, which will help forward it. Now, during this process, when it helps forward the data, we need to check the original IP address we sent, which is in the 10.1.24 subnet. So, 24. The destination IP is in our 40.0.1.024 subnet. However, when reporting back, the source and destination have changed. Now, the destination is the source, and the previous source is our destination. In this case, when I forward it again, the original IP address is 40.0.1.0. The destination is 10.0.1.0, so the devices along the way need to check. Do I recognize 10.0.1.024? Now, here it finds that it has this route in its own routing table, and the next hop points to 30.0.1.1, sending it to R2 from its own J000 interface. At this point, after sending it to R will also check its own table. In this table, there is this destination network segment, and it is sent to an interface of a neighboring router, 20.01.1, from my 0.0 interface. After reaching R1 will also check its own table, which has a route for 10.0.1.024, sending it out from its own outgoing interface. So, in this case, since this is my directly connected route, the next hop will be myself. The outgoing interface is GE01. Let's summarize here. When our router obtains the same IP address from different routing protocols, when it comes to IP network segments and masks, at this point, the router will first go through. The priority is to select the route with the smallest priority for a phone and place it in my routing table. However, if they are all learned through the same routing protocol, the router will choose the route with the lowest cost value. In short, our IP routing table only selects the best routes, and not the suboptimal ones, meaning those that are not as good. When our router receives a data packet, it will search our routing table based on the destination IP address of this data packet to determine what the outgoing interface is and what the next hop is. If it matches these routing entries, it will forward the packet according to the outgoing interface and next hop specified by these routing entries. If there is no such route in its table, it will discard the data packet because it doesn't know where to forward it. Additionally, data packets are forwarded one by one, meaning that all devices along the path from the source to the destination must have a route to the destination. Otherwise, the data packet might get lost along the way. Moreover, data transmission is bidirectional, meaning that there must be a route for both going and returning. If there is a route to go but no return route, then at this point, communication cannot be completed. This is our IP routing table. If anyone is interested in learning about Huawei certification technology or wants to obtain Huawei certification exam questions, feel free to message me.